At some examples last time. We first observed one example we saw was that we take fx to be equal to 1 when x is rational, 0 x is irrational. Then fx is not continuous at any point. Then fx is discontinuous on all points. I'm taking f mapping. Let us take all functions from R to R and everything. Then we saw another example where we took fx equal to 0 if x is rational and irrational, and 1 over q if x is rational and equal to p by q in lowest form. Lowest form means common denominators, common multiples have been removed. And then we found that f is continuous at all irrationals, discontinuous at all rationals. Okay. So therefore, if we define now df for any f, we define df to be the set of all points where f is discontinuous. Take all those points of discontinuity of the function f and call it df. Then in example 1, df is r. At all points it is discontinuous. In example 2, df to the set of all rational numbers. So, the question, one simple question we ask is, can we give an example of an f for which df is a set of irrationals? Of course, a more general question is, given any subset A of R, can we give an example of an F such that df equal to. That is, can you make any arbitrary set as the set of discontinuities of a function? The answer is yes or no. If not, what condition should be? Should A satisfy to get such a function? So given an arbitrary set, will it be the set of discontinuities of a function? If so, tell me how to construct such a function. If the answer no, the A, all A you can't do it, then tell me what is the condition you should satisfy, and then when that condition is satisfied, probably we might have some other to construct. Okay. So this is the question that I want to look at. A more general question. If you answer this question, this is automatically answered. Because if the answer to the first part is yes, this is also yes. If the first part is no, then this will give a condition. I will go and check whether the irrational satisfy that condition, and then that's it. So, therefore, that general question is what? So, first of all, let us start with some simple sets. So, let us look at some very simple case. Suppose A is a finite set, finite subset of R. What is the answer to that question? Now very obvious. You can make simply jumps at those points and all other places constant, so you get automatically a discrete. Easy to see. See that there exists an F mapping R to R, which is such that here equal. So that's the answer. For finite set, the answer is yes. We can always construct a function which is discontinuous. We will move next. Suppose it is countably infinite, a sequence. Case 2. We have already seen one example of a countably infinite set where that is possible, namely the rational numbers. Now we will give a general construction for such sets. So case 2, A is a countably infinite set. So let A be A1, A2, An, etc. Any countably infinite set can be arranged in the form of a sequence. So let the set be A1, A2, A3. But it is not that A1, A2 are ordered. It is not that A1 is less than A2 is less than A3 for rational numbers, for example. It's impossible to order like that. You just arrange in a sequence. So, now we are going to construct. We shall construct F such that E which would then answer the question that up to countably infinite set, the answer to the first question is yes. The real problem starts with uncountably infinite set, and that is what the irrational is asking for. It's an uncountably infinite set. So, the way to define it is define F mapping R to R as F of An to be 1 over n equal to 0 otherwise. Now I will give it as an exercise to prove that this function is continuous at all points except at A1, A2, A3. Well, let me just write this. It is not difficult to see that F is continuous at all points except those. Now, first of all, at least clearly, this is a hint, clearly A is continuous. Every point in A is a discontinuity point because you take any point An, if you take any neighborhood, the value of the function here is 1 over n, but there is always a point which is 0, because all the points cannot be in A is only countable, this set is uncountably infinite, so there must be points from the complement, therefore the 0 value is attained, so the difference is at least 1 over n. We can't bring the difference anything smaller than 1 over n, so choose an epsilon which is smaller than 1 over n and kill the continuity. So the discontinuity at ANs is very obvious. The only thing is now so this is the picture for that. Okay. There is a B belonging to A complement where it is 0. And that's it. And FB minus FA modulus is equal to 1 over n greater than epsilon. We choose epsilon. Choose an epsilon less than 1 over n and then the whole thing. So this cannot be done. You cannot bring it below that. Now suppose you take a point x0 belonging to a complement. There is an interval in that. Okay? Any interval which is, what is the value here? 0. Therefore I have taken epsilon interval about the point. So minus epsilon. Now there exists a n such that 1 over n is less than epsilon. Number of points from A which can fall inside this, so this property is gone. So now the rest of it is obvious. Hence, so you can shrink the interval so that A1, A2, A3, AN are outside. The remaining points are only inside and there the values are less than. So, choose delta such that x0 minus delta x0 plus delta does not contain A1 to A. That's very easy. There are only a finite number of points, they can be easily avoided and you are done. The remaining point the distance is less than 1 over n and you are done. So, I have already put, there is no exercise. Okay. So, we got for, okay, hence df is A, therefore df is A. So, the real non-trivial question is when A is uncountably infinite. So, the non-trivial, this is all trivial part. The non-trivial question arises when A is uncountably. It turns out that the set of discontinuities must have certain structure, and all these fellows finite and countably infinite automatically satisfy that structure. We shall now look at that. So, we shall now analyze the df for an f, how it should look like. So what is our, again recall, df with the set of all points x in R such that f is discontinuous at x. Now what is meant by discontinuous? You are very close to that point, but the difference is going to be not less than epsilon. Some point will have not less than epsilon. Not less than epsilon means it will be greater than or equal to epsilon. If it is greater than or equal to epsilon, it will be greater than or equal to 1 by n for some n. So that's what those points I am collecting. So let me call Tfn to be the set of all points in R such that for every interval, I will write Ix of x. Let me use different notation, psi. There exists, because otherwise I should do two Greek notations, x and y, such that mod fx minus fy greater than or equal to. There are 2 points squeezed in that which try to distance themselves out. Okay. So what is happening is, what is this? Suppose xi belongs to dfn, for only if, what happens? Take the point xi, take any interval I. It may not be centered at xi also. It may be any interval which contains xi. Then there must be at least 2 points x and y where this inequality is satisfied. So there are two, whatever neighborhood you try to take that around that point xi, there are always two fellows who stay away. They don't want to talk to each other. They stay away from a distance of 1 by n. This is somewhat like that discontinuity set, but for a particular epsilon. Now if you put all these things together, you must get the answer for all the epsilon. This is what the, so if you put all this, we expect to get D. Okay? Consider this. Claim okay, we'll see that how it arrives. Claim is that these two are equal. You can do it for smaller and smaller things, put them all together, you will get for all small things. That's what it means. Then, there is one more thing that we will observe. I will have to put claim 1 and 2. All the dn for each n, let me put it this way. For each n is a positive integer here. For every positive integer n. So for each n, dnf is a closed set. This is claim. I'll come back to these claims and prove each one of them. Just indicate the proof. But what is the consequence of it? Suppose these two claims are true. Suppose these two claims are true. What this says therefore is, the set of discontinuities must be a countable union of closed sets. It always must be a countable union of closed sets. So if then we get the theorem, we get that df must always be a countable union of closed sets. Countable could be finite also. Okay. Now all the remaining are empty sets. Empty sets are closed sets. If you want to write anything as countably infinite, take the tail to be empty union, etc. Now we look at the two examples we had. Finite set. There is always a countable union of singletons which are closed sets. Take a countably infinite set. It's a countable union of singletons. Each singleton is a closed set. So again it's satisfied. Therefore in both these cases we had no problem. Df must be, it's a closed set and therefore we got it. Okay. Secondly, we call such sets, we give some name. A subset A of R is called an F sigma set if it can be expressed as a countable union of closed sets. Now F sigma, see basically therefore how does this come about? Where did this idea of F sigma sets come about? The fundamental topological sets are open sets and closed sets. Now you try to build more sets out of them. The only building processes I know are taking unions and intersections or complements. If I take complement of open, I get closed. If I take complement of closed, I get open. Now start with open sets. I put union, I will always get an open set. Nothing new comes. If I take a closed set, and I do a countable union, I may get something different. It need not be a closed set. So I am going to get something new. Whenever you have something new, give a name for it. So that is called F sigma set, which can be a set which can be built by a countable unioning of known sets, namely closed sets. And the sigma there stands for union. And F stands for the first letter of the word in German for closed. What's the word? Does anybody know German? Anyway, I forgot that word. Okay. So that's closed union. Sigma is for union. Then again you take open sets. If you put union, nothing happens. But if you intersect a countable number of open sets, you may get something new. And those are called G delta sets. Delta is always used for intersection. G is again the first letter for the German word open. Okay, we'll stick to F sigma sets. Okay. So therefore, I have not yet proved these two claims. If these two claims were true, what we have shown is that the set of discontinuities must be an F sigma set. So the proposition 1 is therefore we get, hence the set of discontinuities of an F or must be an F sigma set. So that's what we get. That's not the full story. The much more little difficult part, not difficult but more involved part is the converse. Give me any F sigma set, I will construct a function for which that is. Conversely, we can show, this I am not going to, maybe, may not be. Conversely, we can show that given any F sigma set A, there exists an F mapping R to R such that I was just telling people that long time back I gave a 2-year course on analysis. Every one of these things was completely done. All these examples, even this converse part of it. Ranari was one of them who attended that course. He maintained very good notes. And he made the blunder of giving his notes to me once and I lost it. In the sense that somebody else borrowed it and never returned. And Ranari writes a beautiful handwriting and kept them all in neat, bound, long notebooks. They gave me about 6 volumes or 7 volumes of it. I kept it saying that I will get it all sorted out and get it typed as a lecture notes and we can always keep it as a reference. But I never got to it and lost the notebooks also. Criminal. At least he would have had the notes. So never ever give your notes to me. I lose it. Okay. So therefore what do we get? These F sigma sets precisely capture the essence of discontinuity. It is the F sigma set which captures the discontinuity. So therefore, if you want to see whether I can construct a function with this set as the set of discontinuities, all I have to see whether it is an F sigma set or not. So the question about irrational sets, the question therefore is we will have to check whether the irrationals are an F sigma set or not. That is another story. We will come back, we will come to that later. So let's therefore get back to these claims. Or maybe I will complete these things and then write each one of these claims. Okay. Now, are the irrationals, okay, let me write this. Combining these two, hence, we have the theorem, a subset A of R can be the set of discontinuities of an F mapping R to R if and only if, because no converse is also, if and only if A is an F sigma set. For example, if you give me any closed set, for example, you give me a closed interval 0, 1, I can always construct a function which is discontinuous precisely in this interval 0, 1 and continuous everywhere else. And you give me, because why? Because a closed set is an F sigma set, it is the union of singleton union of closed sets. You give me two closed sets, a closed interval and a point. Their union, there. Now I can construct a function which is precisely discontinuous in the interval and that point and continuous everywhere. So all such things are, we are able to manage. The construction one has to see, okay? It's not, perhaps we look at this, maybe, you know. No, that's why if you get into it, analysis is one of the most beautiful subjects. Trying to construct these examples and see the ideas that are there, that is simply fantastic. Okay, so now let's look at this, what was that? Hence this theorem. Now therefore, hence the question, I'm writing things now without proving. What is our conclusion? And finally I will indicate. So these two claims have to be proved. The rest of them follow. And this I am not going to prove. So I will box all those which have not been proved. And that I may or maybe I will sometime, I will indicate, after some time I will indicate how to construct these functions. Okay. Hence the question about constructing an F for which df equal to I, the set of irrationals, boils down to finding if I is an F sigma set. If it is, then we can construct. If it is not an F sigma set, we cannot construct. It's a clear-cut answer. Okay. So therefore, we should know something about F sigma sets, little more than just the definition. I'll look at one property. One property of F sigma sets. It's a very important property. Now, in previous set of lectures, I discussed something about categories of sets and the Bayer's category theorem. Okay, and if you forgotten that, go back and refer to the lecture notes or the videos. The definitions are there. So I will just briefly recollect what I said. Will recall. First, we had the notion of nowhere dense. So what was the definition? I will look at various ways. A is nowhere dense. This is one of the ways of seeing it, but I had a more intuitive way of seeing it in much better. But I will use only this. Set if its closure, that is smallest closed set containing A, is called the closure. If A closure, the closure of A, and this is not necessary in our application because we will be dealing with only closed sets for whom the closure itself does not contain an interval. This is one way of looking nowhere dense set. The closure of A does not have an interior point. If it had an interior point, it would have had an interval also along with. So it does not contain an interval. That is the notion of nowhere dense sets. Then we say a set S is of first category if it can be built through such sets. If A is countable union of S is countable union of nowhere dense sets. Countable union of nowhere dense sets. Then it is called a set of first category. Then we said a set is second category if it is not first category. This is the easiest to understand. It is not first category. There are only two categories. Okay. First category or second category. Second category if it is not first category. Now what does it mean to say that it is second category? That means it is not first category. It is not first category means it is not the union of nowhere dense set. That means if it is the union, then one of the fellows in the union, the closure must have an interval. So that means, that is, A is second category if whenever A equal to union Sn nowhere dense, A equal to union Sn, then at least one Sn closure has an interval. Because if all of them don't have interval, it becomes first category. Okay, so at least one of the Sns must have an interval in its closure. That is called second. That is the notion of second category. And fourth, first category union first category is first category. If you take two sets of first category and union because this is a countable union of nowhere dense sets. This is a countable union of nowhere dense set. The union is still countable union of nowhere dense set. So the countable union of countable union is still countable union. So this is still a first category set. The most final blow or one of the most fundamental theorems, powerful theorems in analysis, topology, and is that a complete metric space is of second category. Now, all we need is for our purposes, R is of second category. This is the recall part of it. The real line is of second category. If you remember all this, now let's go back and ask these questions. What can you say about Q? Is it first category or second category? Well, I can write Q as the union of Sn, where Sn is a singleton. I can arrange the rational numbers as a sequence Q1, Q2, Q3, Qn, and I can just take Sn to be Qn. Now what is Sn closure? Itself. Because it's a single point and it has no interval, and therefore Sn are all nowhere dense. So it's a countable union of nowhere dense set, therefore Q is Q is first category. So what it says is the following, that any countable set must be nowhere dense. Must be first category. Because it's a countable union of singletons and they are closed and have no interval sequence. So rationals are first category. Therefore, irrationals are of second category. Irrationals are of second category, isn't it? Because if that is also first category, then the real number is I union Q. First category union first category will become first category, which is a contradiction of Bayes' theorem. So by Bayes' category theorem, irrationals are forced to be a second category set. Right. So that is the observation that we make. I have not yet come to. I will just erase only these things. These are things that. So I'm just giving an outline. Okay. So what is going on? Right. So now I have not yet come to. I said I will come to look at an important property of F sigma sets. I have not said what that important property of F sigma set is. It turns out, we'll see why it's not difficult to see. Every F sigma set, this is a theorem, not a difficult theorem at all. We will see this in two lines of theorem. Every F sigma set is either first category or contains an interval. It must be one of the two. Either it contains either it's a first category set or it contains an interval. Now I does not satisfy any of this. I is second category, the irrational. It does not contain an interval and therefore I cannot be an F sigma set. Okay, so this is this is a theorem which I have not proved, and hence, since I does not contain an interval and is not first category, it cannot be an F sigma set. Therefore, cannot be the set of discontinuities. So you just cannot, nobody on earth can construct a function which is discontinuous precisely at irrationals. But there is a lot of the topology of the real line that is built into there. Everything gets connected. There is something, closed sets living somewhere there, nowhere there sets living there, first category thing, Bayes' theorem living somewhere there. But they all get connected in answering one fundamental question as to whether we can construct a function. And so that's why these are very powerful theorems, in the sense that they bring in so many properties of the real line into unison to give the answer. Right. So now what are the things that I have left unproved? So I am somewhere still here. This claim I have not proved. And then if I prove that claim, then I get all these things. Then the converse part of it is not proved. Then I have not proved this, and so on. So let's go on somewhere, the remaining part, quickly see what are all the things that we can do about it. Let's dispose of this first, easier ones first.
Excuse me, sir.
Yeah.
Sir, should we take recourse to this novel dense sets all the time when we want to prove this theorem, or is it just sufficient if we consider the convergence of Cauchy sequences?
Where?
Because when we say that according to Bayes' theorem, a complete metric space is second category.
So it connects the convergence of Cauchy sequences and the category. You see, it connects the convergence of Cauchy sequences to category. Right? So it's not, you can't take recourse of one, these two are linked. If this should happen, that should happen, if that happens, this should happen. It will be of a second category. If you have a complete metric space, the fact that main essence of it is that Cauchy sequences converge. That forces the category to be second category. it does not mean that every second category set is a complete matrix. Complete. Because irrationals are second category and they are also only missing things. Okay. Now let's look at dispose of this. So let me call this as claim 1 as A. I forgot what A. This is B and this is C. This is the order in which they came. C and this is D. These are the things that I am not doing. Now let's look at the D part of it. So I will now erase every one of these things that. So if you look at the D part, it's very easy. It claims that if you have an F sigma set, it is either first category or it contains an interval. Suppose it is not first category. Okay. So let A be an F sigma set. Hence, A must be equal to union of AN closed sets. Okay, because any F sigma set is the union of countable union of closed sets. Right. So there are two possibilities. Whenever you have two possibilities, you have to show that if this does not happen, this should happen. So suppose A is not first category. So if that does not happen, the second one must happen. Suppose A is not first category, then
doesn't it mean that it is second category? Because
yes, exactly.
okay.
But I am not claiming that all F sigma sets are second category. If it were not first category, it may be first category. If it is not first category, it will become second category, which will force this. Then A is second category. Therefore, one of these fellows must contain an interval. Therefore, for some n, AN closure must contain an interval. But AN closure is AN itself because ANs are all closed sets. That is, AN must contain an interval because AN is closed. So therefore, there exists an interval contained in AN. Because AN is contained in, which is equal to, so there exists an interval which is contained in. So either it is first category, or if it fails to be first category, it better contain an interval. So it's a very trivial result. It's a very useful result. That is how we interpret that result to see clearly that irrationals cannot be an F sigma set. So therefore, either this, or if it fails to be this, it is this. So therefore, every F sigma set is either first category or second category and hence contain an interval. Second category is a trivial conclusion because it is not first category. But the structure that it is a union of closed set forces it further to contain an interval. Okay, so that disposes of D. Now let's come to these fellows. Now let me recollect the definitions again. Df is the set of all x belonging to R, so that f is discontinuous at x, and dnf the set of all xi in R, such that for every interval I xi containing xi, there exists xy in I xi such that mod fx minus fy is greater than or equal to 1 by n. This is our definition. Okay? These were the two definitions of the two sets we have. Now let's look at claim 2. That's even easier. So let us look at claim 2. We want to prove that DNF is closed. If you want to prove something is closed, we must show that all the limit points are there. So if some limit point is there, we must show it is there. So, okay, suppose there are various ways of looking at closeness. So we will use whichever is convenient. So suppose xi is the limit point of df. We want to show that xi belongs to. That is the idea of showing that something is a closed. Now, if we want to show that xi belongs to this, we must show that this property is satisfied. So that is to show that for every interval I xi containing xi, there exists xy in that interval such that mod fx minus fy is greater than equal to 1. This is what we want to show. So you first know what it, moment you go on writing what is it that you want to show, you realize that there is nothing to show. Okay. This is clear, very trivial more or less. Now, what does that mean? So start with any interval I xi. So let I xi be any interval containing xi. So here is xi, that is xi. So the xi need not be the center of that interval. But whatever it is, we can always find an epsilon such that xi minus epsilon, xi plus epsilon is inside that. So you can always find an interval inside that. So therefore, there exists epsilon positive such that xi minus epsilon, xi plus epsilon belongs to I psi, I must call it. So I am taking any interval about the point xi, and inside that interval I am structuring a sub-interval such that it is centered at xi. I have not yet used the fact that xi is a limit point. What is meant by xi is a limit point? There is a sequence of points which are going to converge to xi. Okay, since xi is the limit point of DNF, there exists a sequence xi k belonging to DNF such that xi k converges to xi, because the limit point of this. Now, if xi k converges to xi, eventually all the xi k's will come and fall here. Okay. So therefore, for large k, all xi k will be in xi minus epsilon. Agreed? Now, if all of them fall, at least one of them is there. So pick any one of them. So therefore, pick a xi k. Therefore, xi k belongs to I xi also. Right? Because I minus epsilon, xi plus epsilon is sitting inside I xi. So therefore, I xi is an interval containing xi k. Therefore, I xi is an interval containing xi k, and xi k is in DNF. What does that mean? Whenever somebody is in DNF, the moment you put an interval about them, you will find those 2 points x and y. Therefore, there exists xy in I xi such that mod fx minus fy is greater than or equal to 4. So I didn't know how to handle xi, but I brought in the fellow whom I know. This is the trick. I always say that you don't know something, you go to something which you know, and from there you get the answer, which proves star. So that's what star is. Given any interval I xi, you found the 2 points and that fx minus fy is greater than or equal to 1 over here. So I am going to leave this as an exercise. So what of course this C, I really do not know whether I will construct this example, but let me see whether I can at least indicate some time when we come back. So therefore, we have a very clear-cut statement about how discontinuities can be. There is a method in madness also. It just cannot be arbitrarily discontinuous at arbitrary set of points, and there ought to be certain structure even in the set of discontinuities. This is in a sense a very, very fundamental theorem in that sense about continuous functions. See, not only you know about continuity now, you also know a certain amount of structure about discontinuities. They cannot be very bad. And as we go along, we will find that if you put more better functions, the structure of the discontinuities become even better and better. We have much better control over the discontinuity set and things like that.
Sir, we are talking of only functions from R to R here.
This is real analysis. Okay, I'm not talking about analysis. I'm once in a way trying to point out, but now see whether you can generalize these proofs for a metric space situation. There may not be much difficulty at all. Whenever you put an interval, you put a, and whenever you want to give those DNF, what will be your definition of DNF? You won't say for every interval IISc containing Xi, you will say for every open ball containing. So, and show that each one of them is closed. Again the same idea. So really these are only indicative, but actually if you change the notations properly, they carry over everything. Or you can push it all the way up to metric spaces. So therefore, let me sum up. If we have f on an interval mapping I to R, and if f is continuous, then we had all those nice properties. What? Intermediate value property is one of the most important. And therefore, range of f must be an interval. Okay, that's one of the most important properties of a continuous. And then if I is a closed bounded interval, in addition, we get f as max, absolute max, f as absolute min, and range of f is precisely the closed interval max, min to max. That closed interval is the range of f. All the values in between are taken because of the intermediate value property. Alright. If f is discontinuous, then dr must be These are some of the fundamental properties of continuous functions. Of course, we had many other things. F inverse of an open set is an open set, other things. We set up all points where fx is greater than k is an open set, less than k is an open set, equal to k is a closed set, and so on and so on. Let me write that. F inverse, this is one, all this. F inverse of A is an open set in I for every or then for every k in R, the set of all x in I, that fx less than k, set of all x in I, that fx greater than k, open sets in I, and the set of all x in I, that fx less than or equal to k, the set of all x in I, that fx greater than or equal to k, or closed sets in I, because because of the complementarity. This is the complement of that, this is the complement of that. And the intersection of these two, the set of all x I, fx equal to k is because it's the intersection of two closed sets. And most important, in particular, the set of zeros, in particular, the set of all zeros of that function, roots of that function, form a closed set. These are all nice properties of a continuous function. Okay? That's why people hang around the continuous function. There is a lot of information that is available. Right. Next I will look at briefly about convergence aspects. Okay, then even before that, let me now look at it a little more. So suppose now I have the closed interval 0, 1. Suppose I take I to be the closed interval 0, 1. And I take any function from I to R. Okay? Then we have the fact that if we have a closed interval, it's a bounded interval, the function takes a maximum and a minimum. Therefore, then what can we say about defined as g of x is equal to mod f. That will also be continuous. Okay. It's not very difficult because mod gx minus gx naught is less than mod f is equal to mod f x minus mod fx naught, which is less than or equal to mod of fx minus fx naught, and that can be made small. So that's fairly straightforward. This is also a continuous function. So it is a continuous function, therefore it has a maximum and minimum. So define m f to be the maximum of mod fx where x belongs to 0. This makes no sense. Uses m to be the maximum of this function. So for every continuous function on 0, 1, we have associated a number, mf, which is equal to the maximum of that function, which is between 0 and 1. Now what can you say about that function? Certainly it is greater than or equal to 0, because the maximum of some non-negative quantities. And when will it be 0?
0.
The maximum must be 0. That means at every point mod fx must be 0. That means at every point fx must be 0. That means it must be the 0 function. So, if and only if, when I write like this without the x, that means at all points they are equal. Fx must be equal to the 0 function x. So f must be the 0 function. Then, take any constant, real constant alpha. If f is continuous, alpha times f is also continuous. These are very trivial verifications. And therefore I can talk about the m alpha, which is the maximum of x belongs to 0, 1 of mod of alpha x, which is equal to the max of mod alpha into mod fx. And since this mod alpha has nothing to do with x, it comes out. And therefore it is mod alpha into m. Okay. Now we will look at, if f is continuous, g is continuous, f plus g is also continuous. So you can look at the maximum of f plus g. So for any x, we have mod fx plus gx is less than or equal to mod fx plus mod gx. That's triangular inequality. But mod fx is always less than or equal to its maximum. Mod fgx is less than or equal to mg. So for every x this is less than or equal to, so therefore this is a bound, therefore the mf plus g will be less than or equal to mf plus 2g. The least upper bound of that. So therefore it will be less than mf plus 2g. Which simply means that mf acts as a norm on this space. Therefore mf is a norm on the space of all, the vector space of all continuous functions on 0. This is denoted by C. Well, maybe I should put R to say that the real value functions on 0, 1. Okay, CR0. So that's a non-linear space, the space of all continuous functions with this norm, namely the maximum norm, which is denoted by CR01. Now we can talk of functions on this matrix, because once it's a nonlinear space, we can talk about continuity of functions defined over that nonlinear space. For example, we can look at functions mapping function from one metric space to another metric space. I take both these metrics, I looked at R to R. Now I pull the role of R and make it CR01, and on the codomain set also I pull it out and make it as CR0. Or I can talk about on one side I have the space of continuous functions, and on the other side I have the real numbers. Such things, such functions are called real linear functional, I did say real functionals on CRs. If the values taken are scalars, we call them functionals. Okay? And the delta function is one such function. It picks up the value at the point 0. So f of f mapping CR01. Let FA mapping CR01 to R defined as FA. See, what should it do? With each function, it should associate a number. So FA of f is equal to f of a, where for any a. Define FA to be this. So what does it do? It filters out the value at the point a, and that is the delta function. This is it's a functional. So this is called the delta functional. Delta x minus. It picks out the value at the point k. So the delta functional, if you want to call it a function, it's not a function from R to R. It is a function from some space of functions to the scalars. Its domain is a collection of functions. Its range is its codomain is the real numbers. Now we can ask about continuity of such functions. I could put some other thing also. I could put CRAB, CR14, 15, whatever it is. You can just make any number of such. I can put one metric space and another metric space here. Now I knew this. I got a new metric space, so I want to play with it for a while. So therefore, CR01. Now I'll give you an example. We already seen this filtering the value at one point is analogous in the discrete case. If you have a finite dimensional vector space, you filter one particular component, okay, and purge all the other components, and that is the role. It's there. Now we have a continuum of components, and we are filtering each one of these components to this delta function. So it's essentially some kind of a component identification, component picking. Now let's look at this simple example. So analogously, let phi x be any fixed function in CR0. Define a map from CR01 to CR01 as, what should it do? We should take a continuous function and convert it to code it as another continuous function. That's all. It should take a continuous function and code it as a continuous function. So it takes this continuous function f and it must code into another continuous function which is simply f phi. That is, the coded function evaluated at the point is simply the product of fx with phi x. This pointwise multiplicative function. Now if f is continuous, phi is continuous, f times phi is also continuous, so therefore it is definitely a map from C01 to CR01. Now is this map continuous? These are the type of questions I will be investigating. Is phi a continuous map from CR01 to CR0? See, now this is where we want to see whether we understand the definition of continuity properly. What does this mean? I'll look at this next class. But what does this mean? This means that I want to look at the continuity at a point first. At every point I want to look at the continuity. Which point? A point in the domain. The domain itself consists of, these points are all functions. So I must take a point which is a continuous function f and see whether phi is continuous at that f. How do I see it? I look at phi f and construct an epsilon neighborhood of it. What are epsilon neighborhoods now? You hold all about that, or take all those continuous functions, and there, whenever you construct a similar neighborhood around f, the values of phi must fall in that. What does it really mean geometrically? That's what we will see. Okay? So these sort of things over the continuity of a function defined over general metric spaces. This is a concrete example. As we go along, we will pick up more and more on such spaces. Okay, I'll stop here and then I'll pick up from here. I left some of those things unfinished, but the line of thinking is that you break this discontinuity into smaller sets, find each is closed, the union is this, therefore that uses the notion of F sigma set, and identify the pillars. So really the most important thing is continuity is one thing I know, and discontinuity I have a control, which is not so bad as I originally thought. That's the sobering thought.